Whoa.
I was gonna say, I got a text for the trucks. I was like,
Okay, let's see. Sarah B. Yeah, okay. Claire. Matt. Luke. Jaden. Emma. Right. Liza. Stuart. Ethan. Manya. Olivia. Kashal. Diego. Darwin. Sean. Jules. Doa. Matthew. Colin. Emily. Rennick. Sarah T. McKenna. Okay, is there anybody here whose name I didn't call? Got everybody that's here. Okay, good deal. Whew, made it. Oh, yeah. Okay, time to get started. So real quick, let's talk about schedule just a little bit. Here we are today is Wednesday, and notice the exam is the very next class meeting, right? So exams on Friday. Yep, exactly. A lot of excitement. I hope everybody's taking appropriate, last shot studying. This is studying time for the exam. But I do want to remind everybody, the best plan is to be studying for the exam continually as we go through the course, right? Don't think of studying as something that's done at the last minute. There is a surge of studying at the last minute, of course, but try to, after every lecture, your goal for the next couple of days is to get ready to take a test on that material. And I talk about that at length on the website, but anyway. Okay, notice then also for today, whatever sections we put in here, that's colored in yellow, not green. That means it's fair game for exam 2, not exam 1, right? So that makes today kind of a weird day because it's, right before exam 1 and the material is not relevant to the exam. So it's an unavoidable reality of a course that's packed and I can't, we just don't have enough time in the schedule to be able to set aside a day for review or something like that. I guess the other possible solution would be to make today's material fair game for the exam, but I don't think anybody wants that. So, right. So anyway, a little bit weird, but don't forget the material for today is fair game for exam 2, and it's right after spring break, which is really not that long from now. So we're still worth paying attention. Yes.
So does the content for exam 1 stop at 2.4?
Yes, at 2.4. That's right. No, it's very rare for me to cut a section in half and say, well, the first half of the section's fair game. It's just easier to just draw a line, and yeah, right. Nice clean line. Yep. Okay. All right. So anyway, let's get back into the material. So I'm gonna rewind just a little bit and talk about the second derivative stuff that we already did. Why not? Don't forget, if you have a function of x and y, its partials are also functions of x and y, and you can note so on your diagram. So just as an example, suppose we're looking at z being a function of x and y, and r and theta are polar coordinates. Well, that is just a fancy way of saying that x and y are functions of r and theta. Right, so this is the diagram is basically described by the givens here. Then how do we take, for example, the partial of z with respect, let me do a better color choice here, the partial of z with respect to r. Well, there's z, there's r, and you see we have two paths. There's the x path, thus giving the x term, and then there's the y path, thus giving the y term. Okay, does everybody see how that works? Right, it's a nice organized little process, and this is the way I always think about doing when I'm computing a single partial derivative. That's the way to think about it. Yes.
Why do we need both and not just one or the other?
Yeah, because changes propagate in both directions. Or along both paths. So when r changes, that does cause x to change, and that change in x does cause a change in z, but that's not the only way that changes come to z, right? It is also unavoidably true that if you change r, then whether we like it or not, y is changing too. Oh, whoops, I just messed up. R is changing, y is changing too, and that also contributes. Yeah, does that make sense? Yeah, cool. Good. Anybody else? So you can compute a couple of these partials. So for example, the partial of x with respect to r, well, we know the formula for x in terms of r and theta. It's an easy partial, so that's no problem. And then likewise, the partial of y with respect to r, that's easy. Just a little bit of single variable calculus effectively. And so here is our first partial with respect to r. Okay, notice that in the formula for this first partial, there's a new thing in here. It's this thing called zx. Zx, if I take a second derivative now, I'm going to need to at some point be taking the derivatives of zx, and I don't see zx on my diagram, my existing diagram of variables that were previously discussed. So no problem, just put it on the diagram. It's as simple as that. Just recognize that it is a function of x and y, just like z is. So they're so indicated, right? I mean, I have here zx, function of x and y. And then, of course, likewise for zy, also a function of x and y. And very helpful for when you take the next step. I'm going to do the second derivative. Where let's see here, we already computed partial of z with respect to r is that. The second partial of that, well, the second partial is the r partial of that thing, of course. And now we find ourselves, minor detail. Don't forget cosine theta. While you're taking an r partial, r is your variable. That means that theta is a constant. That means cosine theta is a constant. Treat it as a constant, and of course, constants factor outside of derivatives. So likewise, sine theta is a constant. So that factors out as well. I'll point out that it kind of at a glance was actually starting to look like we were going to have to deal with a product rule here, doesn't it? And but we didn't. So lucky break. For whatever it's worth, that was a lucky break. You can't count on that happening. Very often, this thing over here, this other factor, is not a constant. And if you want to see an example of that, and I think this is a superb exercise, and I'd like to encourage everybody to try it. We're going to go through and finish here the computation of the second partial with respect to R. If you do it with respect to theta instead, the theta partial, then you do not get so lucky, and you have a product rule thing that you have to do here. So, okay. Yes.
Where did the ZX come from?
Yeah. So here was our initial chain rule. And well, this is just a partial of Z with respect to X. And I just chose to rewrite it as ZX because it's notationally a little bit more compact.
Oh,
That's
so
all.
like Z with the subscript.
Yeah, that's Z. Oh, that's a subscript. Oh, no. Yeah. No, sorry if that's not clear. It's intended as it's conspicuously smaller, et cetera. Yeah. Z partial with respect to X. Okay, so here we are then looking now at partial of ZX with respect to R. And so many students get thrown at this point because let me show you just, for example, one thing some students will write. They'll say, well, we had Z, we're doing a partial, and then now we're doing another partial. So how about I write that as ZXR, right? What's wrong with that? Can't I just call it that? And no. You can't do that because Z is not a function of X and Y and R and theta. Let me color choices. Z is a function of X and Y. It's got two input variables. I suppose you could alternatively think of Z as, in composition as being a function of R and theta, another two variables. But it's not a function of these four variables together because these are not independent, right? And so, for example, you can't say, oh, I'm going to take the partial with respect to R, because if you're taking, if these are your variables, and if you say partial with respect to R, then you're saying you're going to change R, but you're going to hold all the other variables constant. That doesn't make any sense. If you change R, you can't just decide you want X and Y to be constant. They're not. Right? So anyway, point is, it just doesn't make any sense. So don't make this mistake. Very common mistake I see on exams all the time, and it's always a tragedy when students write, ZXR. That's not a thing. Right? You can talk about ZX. You can talk about ZY. This is nonsense. All right. So rather, let's just recognize what we're actually doing here. When we're taking the partial of ZX with respect to R, well, there's ZX, there's R, right there on the diagram. Good thing we supplemented our diagram. I can then see what I'm doing. I can see that there is a path there through which changes can propagate, and there is another path there through which changes can propagate, and I can write down the chain rule again. There's the Y term, there's the X term, and notice that in all cases, we're talking about partials of ZX. We're talking about partials with respect to R. All that changes is that here X is the intermediate variable, here Y is the intermediate variable. In recognition that we have these two intermediate variables, that's it. And then, of course, we have to take it from there and simplify, but that's the process. Yes.
Can I just clarify why do you put the ZX and the ZY underneath the Z and like how you do it right there?
The Z, where are we?
In your drawing next to number 2.
Oh.
When we added the ZX and the ZY,
Yeah.
you know to add it there.
There, yeah, right. Because if you have Z as a function of X and Y, when you take its partials, those partials are also functions of X and Y. And so functions of X and Y, I have to indicate as functions of X and Y by putting them, you know, to the right of X and Y. Because X and Y are not functions of them, right? And we're drawing functions here as going left to right. Is that cool? Does that make sense?
I think so.
Okay. Yeah. Yeah. I mean, we say that the lines have to go left to right because the alternative is just, it'd be terribly confusing. So always draw your functions, you know, left to right. Sometimes people like to do them bottom to top but certainly on any given diagram, decide which direction is the, the progress of the functions and stick with it. Yeah. Yep. Yep. Okay. Yeah. So let's see here. So the partial of ZX with respect to R. Oh, come on, stylus, is described by these two paths, thus giving me these two terms. Don't forget, of course, your cosine theta comes along for the ride. And then now, wait a second, let's talk about the partial of ZY with respect to R. All right, well, it has two paths, which give us two terms. Don't forget your constants, comes along for the ride. And so there's that's how the chain rule shows up in this part of the problem. Everybody good with that? Okay, let me erase the first term over here that we're kind of done with. Let's get rid of those, all that nonsense. There we go. And then this is how that second term develops. Okay. So it's all over with the shouting, pretty much. How would I write partial of ZX with respect to X? Well, ZX is a function of X and Y. There's no chain rule to be talked about here. There's no intermediate variables, and it is literally ZXX, and that's fine, right? It's just the second partial of Z with respect to X. So no problem there. Again, a little bit of trig to compute that partial. You know, dot over here, kind of the same sort of things. Don't forget your constant that continues to come along for the ride. Likewise on the other side. And then, you know, you got to combine terms. And so you'll note, for example, the cosine theta. Well, there's two factors of cosine theta for that term. And there's a sine theta and a cosine theta for that term. But then check it out over here. There's also a sine theta, cosine theta over there, which gives me then between the two of them, two of those exact same terms. So that's nice. Simplifies, etc. Everybody with me? Yes.
So just to clarify, you can write ZXX because Z is a function of X, and so is the partial.
Yeah, that's right. If you come up to the diagram and you look at that right there, Z is a function of X. There is no intermediate variable there. So there's no chain rule to be done. And for the same reasons, you know, ZX is immediately a function of X. So there's no chain rule to be done there either. And it really is the same exact thing. I mean, it's the definition really of taking Z and doing its second partial with respect to X. Yep. Z, yeah, well, Z is not a function of simultaneously a function of both X, Y, R, and theta, right? Because that, again, those aren't independent variables. Yeah. Okay. All right. So there you go. The book doesn't actually have any examples of this second derivatives business, and I think that's unfortunate. It is actually really important, and I have an example to show y'all. There's an operator, a math operator called the Laplacian. The Laplacian is denoted with this little triangle thing there. It's I guess it's identical to the capital Greek letter delta. But this is not delta. This does not mean it is a little unfortunate. I'll grant you. This looks like change of f. That's not what it is. This is the Laplacian operator in this context. And in context, you just have to, again, apologies for that. But in the context, it'll be clear. And this is what it is. And it's some of the second partials with respect to the input rectangular input variables. It's much easier to motivate why we would care about the Laplacian in rectangular coordinates. So we write it like this. But as it turns out, the kinds of functions that we want to apply the Laplacians to are very often much easier to describe in spherical coordinates. And so let me show you an easy example of where this comes up. Very often we're interested in the function 1 over rho, which is really easy to write in spherical. And it's, also I could write it in rectangular, but now I've got square roots in the denominator. And right, and I guess if you really wanted to, you could put that in there, that being our f, and you could take a bunch of partials, second partials, but now you're doing partials with the quotient rule and square roots and power rule and chain rule, and it's a nightmare. And I've done it before, and so it can be done, right? It's no fun. It's a page of algebra. Okay, so here's the thing. Instead, there is an alternative formulation for the Laplacian. And it doesn't look friendly, but I claim it's actually lovely. It's very, very nice. This thing here is identical to that monster. And how do I know? Well, because we can use the second derivative chain rule to compute things like that. Right? I can just straight up compute that with the chain rule, just like we did on the previous page. It's spherical instead of polar, but it's morally the same, right? F is a function of x, y, z. X, y, z are functions of rho, phi, theta. You can compute this thing with the chain rule. You can likewise compute that with the chain rule, and you can compute that with the chain rule. And if you combine them per this, you get exactly that. Now, why is that an important calculation? Why is it important to notice that this seemingly not that bad expression can rewrite instead as this seeming bear of an expression? Well, check out what happens. We already agreed that this would be a bummer of a calculation right there, right? Well, let's look at alternatively. I can take f equals 1 over rho, and let's plug that in here and see what happens. If f, let's see here, if f is 1 over rho, okay, well, that means that partial of f with respect to rho is negative 1 over rho squared. And if I put, this into there, then I find myself looking at rho squared times 1 over rho squared. That turns into a constant whose partial is therefore 0. Mwah. Right? Lovely. This partial is immediately 0. This partial is immediately 0. We're done. We just computed this whole monster. Because the function looks nice in spherical coordinates. It looks horrendous in rectangular coordinates. It's lovely in spherical coordinates. So spherical Laplacian is a really good trick to know about. And again, the only reason we know that the spherical Laplacian is written like this is because of calculations that are morally identical to this. So very important technique. And I'm upset that the book doesn't have it in there, but anyway, we're including it into the course by way of it being presented in the lecture here. Yes?
So should we know how to go from the original function to the Laplacian?
Well, now this would be a big exercise, but if you wanted to, yeah, you could absolutely prove this formula, that, that these two things are equal. And let me,
So we would
Come up here.
rewrite each of those as.
yeah, you'd write this with the chain rule. You'd multiply by rho squared, and then you take its derivative, this product's derivative with the chain rule.
Well, I
Right.
just mean like going from that first equation to the.
From this down to this?
Deriving that.
No, I understand. That's what I'm explaining. Yeah. No, you because you kind of do it backwards. What you really do is you go this, right? So you compute this with the chain rule, multiply by rho squared, then compute this partial of that with the chain rule, then multiply by 1 over rho squared, and then you get a bunch of stuff, and then you compute this also with the chain rule, and then you compute this also with, you compute everything, compute all of these things with the chain rule, and then when you combine them together, they'll simplify to that.
So if I didn't have that, would I be able to get it from that?
Reverse engineering it? No, well, I mean, if you're clever, it's really tricky. No, that's not a process that I'm pushing here. The process, the chain rule process is like this. And if you want to go back this way, then it's play with it and notice what you have, and then get clever. And not that it's not doable, but it requires much more cleverness and much less technique. Or, correction, much more cleverness and just as much technique. Yeah. Right. Okay, so I think that's a cool example. Yeah, so let's see here. Moving along now to section 2.6. We're now officially done with 2.5, by the way. So new thing to define called a directional derivative. And I want to motivate it by recalling first what we know about partial derivatives. Everything on the screen here is things we know about partial derivatives. The partial derivative is the slope of the graph. Okay, well, but partial with respect to xi, so slope of the graph in the xi direction. The partial derivative is also the factor. This is the way I like to think about it. It's a multiplying factor. It's what you multiply by input changes to get output changes, as we previously discussed. Again, assuming you're moving in that direction. We know we can compute it with this formula. I mean, you can just kind of multiply that out. Technically, we've never written this down before, but you can confirm that this works because after all, the gradient is just made up of the various partial derivatives. So dot it with a bunch of zeros, and only one of those partial derivatives remains. So that's something you can directly confirm. And the definition of the partial derivative now, this isn't how we wrote the definition, but this is an alternative formulation of the definition. And so what I'm going to say is this is another fact that you can check, and I'm going to take this as a new equivalent and at this point really better definition for the partial derivative. Again, this is worth checking. So use the chain rule. So check it out. We have f is a function of whatever of the inside. The inside is a function of t. So you have a composition there, and take the derivative of that composition with the chain rule, and what you will get is that partial. Okay. So, okay, bunch of facts about the chain rule. Let's get a bunch of facts about partial derivatives. Why are we revisiting partial derivatives? All of these facts I've phrased as being relevant to a certain direction, namely it's the EI vector. That's the vector that's pointing in the direction of xi. It's the vector that goes inside of this new definition. It's the vector that you dot with the gradient. It's the vector that tells you the direction in which, slope of the graph and all that. It's the direction that you move in order to interpret as a factor. So we've got here a bunch of facts that all are kind of simultaneous if you're moving in a certain direction. And with it written like this, I pose, okay, well, is there anything particularly magical about the axis directions? Wouldn't all of these facts still be equally equivalent if I were moving in a different direction? So pick any other unit vector. I'm going to argue any other unit vector. I could still write down. I can still write down this expression, and I can talk about this as a meaningful thing. I'm going to happen to call this the directional derivative, but it's a thing. It's still equal to that. You can still confirm this with the chain rule. It's another good little exercise. Right? Again, you have taking a derivative of a composition, write down the chain rule, you get this. And the interpretation should come along for the ride too. We're doing all the same things. We're still starting at a point A, moving with velocity V, keeping track of the values of the function and seeing how they change. I'm just going now that way instead of that way. Right? Well, whatever. So all the same interpretations come along too. This still gives me the slope of the graph, just now in the V direction, the direction that I'm going. Yes.
Would you mind demonstrating how you can get the d over dt is equal to f of a plus tb using the chain rule? Because I'm not
How to confirm this with the chain rule? Yeah. So what we've got here is f is a function of x, y, z, let's say, and x, y, z are functions of t. Now, specifically, where you can see that is right there. You can see x, y, and z. The things that go into f are all functions of t, right? And then f is a function of those things. Right, so there's the composition. And how do we take the derivative of a composition? Right, you got to, you're taking a derivative now. Taking a derivative of a composition, you do that by the chain rule, and the chain rule turns into this. There's a few. I mean, you got to write down, what exactly the chain rule says here, and then you've got to write down, rewrite that in terms of, as a dot product, but it will assemble into exactly this. And I'm going to leave the details as an exercise because I think it's a healthy thing to sort of write down. But it's literally just a matter of applying the chain rule with this as your roadmap to taking a derivative with respect to t, straight up write it down, right? And it'll simplify to this. Yeah.
So like the df over dx times dx over dt.
Yep. Chain rule. Yep. Absolutely. Yep. Or alternatively, and arguably even more simple, use the matrix form of the chain rule, and it will immediately turn into this instead of having to go turn by turn. So your pick, they're equivalent. Yeah. Okay. Anybody else? Yes.
Could you quickly explain why the gradient of f equals the one on the left? Or like where did that?
You're wondering where this came from?
Yeah.
Well, that's exactly what he asked.
Oh. Okay.
Yeah. No, so literally, you're taking a t derivative of a composition. You write down the chain rule, and it will turn into this. Yeah. Okay. So this thing called the directional derivative, using this notation here, directional derivative, it is defined by that formula. It's computed much more conveniently in practice by that formula. And it's the slope of the graph, just now, again, in the V direction instead of axis direction, whatever. And it is, again, a multiplicative factor. So this thing is the factor you multiply. Again, in the usual way, it's what you multiply by input changes to get output changes. Just like we did up here with the partial. So directional derivatives, I mean, I think the best way to think about directional derivatives is they're just kind of partial derivatives, just, you know, in a direction that's not along an axis, but it's ultimately the same thing. And so some supplemental comments, you know, the slope of the graph, well, if I'm at this point and moving in the V direction, so I'm at this point, moving in the V direction, then slope of the graph. So take the cross section in that direction. Cross section is a curve. It has a tangent line, slope of that tangent line, just like with partials. Okay. All right. And now one other point of view I want to give y'all is how to interpret this. It's a nice little alternative interpretation. If you think of, you know, the factor that you multiply by, well, you know, input change, be it ds or ds dt, to get output change, be it df or df dt. Notice, in order for the single variable calculus to work as it's supposed to, right? And you know, let me commit a little math crime there, but you know what I mean, right? You kind of cancel the DS's, and likewise here, you know, again, little math crime. In order for you know, we know that that's what the answer is supposed to be, and we know that this is what the answer is supposed to be. That actually gives us a nice alternative interpretation of the directional derivative. Directional derivatives you can think of as being df ds. It's how fast the function changes per unit distance as you move in a certain direction. And sometimes you're interested in that. So here's an example. Suppose you're driving along a road and you ask the question, how fast is the altitude of the road changing as you drive along the road? Reasonable question, right? Well, I mean, as stated, you're driving along the road. It depends on how fast you're driving, right? If you're driving really fast, then altitude's changing fast. If you're driving slow, altitude's changing slow. So if you then roll your eyes and say, that's not what I meant, I want to know, come on, how steep is the road? What's the rate of change with respect to, forget about me. This isn't about me. It's about the road. So as I go along the road, per unit distance along the road, factor yourself out of the equation, right? Per unit distance along the road, directional derivative gives you that, you know, rate of change with respect to distance. So very natural thing to be interested in. All right. Okay. I want to note, in order to do this, in order to make sense out of this, in order for this to be a reasonable claim, the standard basis vector that I'm replacing does have to be replaced with another vector that's really just like it, just with a different direction. And just with a different direction, another way to say that is has to have the same magnitude. So this has got to be a unit vector to be able to draw these inferences. And this is part of the definition then in this book, part of the definition of a directional derivative. If you want to say this and use that notation, it is required and implicit that we're talking about a unit vector direction. Okay. All righty. So example. Here's a function. Suppose I want to know the slope of the graph. Your instinctive knee-jerk reaction is to think, oh, partial derivative. But we are not moving along the x, axis, or in the direction of the x-axis or in the direction of the y-axis. We're at this point, but our direction of motion is this. We're moving at some sort of an angle, in the direction of 3, 4. So I can't say partial derivative. But again, when you think, when what you're looking for is kind of like a partial derivative, but just in a different direction, what you want is a directional derivative, right? So slope of the graph, directional derivative. We just have to compute the directional derivative. And that's a couple of details to do this. Now, don't make the mistake of plugging in this as your vector, because, well, that's not even a unit vector. So you do have to unitize that vector first, right? You've got to divide by the magnitude, get the unit vector pointing in that direction. So that's what goes there. And heads up about that, right? You can't assume that the things that you're given are exactly the things that you need, to notice a little dirty trick I pulled. I even called it V, right? And you come back over here and I had called it V here. Letters don't mean things, right? So heads up, do realize you gotta make it a unit vector to use these properties. So make it a unit vector. Directional derivatives are computed by dots with the gradient. That unit vector is that. The gradient, well, let's see, I can take my function and take its various partials. The gradient becomes that, which at the point in question is that. So don't forget, we're at this point 3,1. 3,1 is what goes in there to be evaluated, or you might say it's where I'm evaluating that gradient. And arithmetic and answer. I forgot what color I used for the, okay, I'll use yellow. So the slope that we were looking for, namely the directional derivative, we computed that. Arithmetic. Yes.
When you say don't conflate the phrasing with toward the point.
Oh, yeah, I was just getting around to talking about that. Thank you. Let me, yeah, this is unfortunate. It's just a phrasing thing, so you got to be careful about this. And by the way, if you ever on an exam think that the phrasing might leave a little sort of like, wait a minute, what did he mean by that? Then you're very welcome to come up and ask for clarification. But anyway, so at the point 3,1, about like that, right? There's 3,1. When I say in the direction of the vector 3,4, well, the vector 3,4 is like that. This is the vector 3,4. It's a mistake to say, oh, well, where is that vector? Vectors don't have locations. You can't talk about going toward a vector. Vectors aren't anywhere. That's like trying to go toward blue. It doesn't have a location. It doesn't make any sense, right? So, but some students will make the mistake of thinking, okay, well, the vector interpreted as a point is that point. And so let's talk about going in that direction. And that's not what this means. Right, so that hinges on a misinterpretation of what 3,4 is in this role. So yeah, does that make sense? So if I want you to think in terms of starting at a point and going in the toward another point, I won't say it like that. If I want you to interpret as going toward another point, I'll say the point. Toward the point, such and such. Is that clarifying?
Yeah.
Yeah.
You just like basically create a vector like between the points.
Yeah. That's right. If it were this, then yeah, you would subtract and then unitize, normalize, they call it. And then proceed. But again, not what this question was asking.
And if it were referring to a point, it wouldn't have like the dashed line over it, right?
Oh no, I very often will use the same notation to represent a point when even if I'm using, because we do conflate these notations because it's very convenient to just, let the context make it clear. So the clarifying context here is I said the vector, right? And that's how you know that that's wrong and that's right. Yeah. But yeah, you're right. I did. Even describing it as a point. In fact, you can see it right here. The point And I do use that notation, yeah. Yeah. And you know that I'm interpreting this as a point because I say at, and at means location, and points have locations and vectors don't, yeah. Okay, so just a little warning. Okay, another example, I think, yeah. So here, this isn't about graph. This is about how fast something is changing. And suppose that I know temperature is a function of position, which it is, right? I mean, it could, maybe it's warmer here and it's colder over there, you know, whatever. Temperature is a function of position in 3 space. And I can't draw the graph. There's 3 input variables, 1 out. That's 4 variables. I can't, that's, you know, I can't do that. So forget about graphs helping you in answering this question. But it remains, be nice to know, as I walk in a certain direction, you know, as I fly in a certain direction, whatever, you know, as I go per unit distance, how fast is the function changing? Independent of my speed, right? Let's not talk about my speed. I just want to talk about the function itself in a certain direction. What's its kind of rate of change? So we want dTds. dTds is the other interpretation of the directional derivative. And so again, just, you know, you compute the directional derivative. You got to compute the gradient. Yeah, there. Got to compute the gradient. We need the unit vector version of the vector we're given. So we have to, you know, unitize. And this is, again, another important step. This vector is not the same as u. Right? You got to divide that by its magnitude. And apparently the magnitude is square root of 29 there. And then dot product and answer. Is everybody on board? All right. Okay, so a little bit of another apology about labels. Sometimes notations are unfortunate. Sometimes terminology is unfortunate. Here, the term directional derivative is not universally agreed upon what it means. So in some contexts, and by the way, perfectly respectable contexts, I mean, outside of the context of Math 219, I think I'm in this camp here. It's not required to be a unit vector. Now there's consequences, right? You can't just change a definition, but I don't want to have to check certain properties, but I want to have all my conclusions. No, you don't get that. So there's consequences. And if you know, with this, you do not get 1 and 2, properties 1 and 2 that we have over here. So, yeah, you take away the unit vector requirement, then you do not get to interpret it as a slope of a graph. It isn't. You do not get to interpret it as a multiplicative factor. In other words, you don't get to interpret it as ds dt. So that's a steep price to pay. On the other hand, very often you're interested in the scenario of, look, I'm at this point and I'm moving with a certain velocity, and yeah, non-unit vector actual velocity. And as I move with that velocity, I'm interested in some function, and in particular, how fast it's changing. It's a very, very natural thing you want to talk about. This equation right here, perfectly fine. It's just the chain rule after all, right? So you still get a useful concept, and you still get that it's computed with a convenient formula. And in some contexts, the word directional derivative, same word, same notation, is used to mean this, well, importantly, you know, slightly, but importantly different thing. So, and come to think of it, I had this already written down here. But I'm going to say in Math 219, forget about this. In Math 219, the word directional derivative will always mean with a unit vector. Because that's the formula the book uses, and we've just got to, we can't have a just perpetual confusion. So in this course, unit vector is always required. But I just culturally point, after you get out of Math 219, depending on who you're talking to, if they say, well, you just compute the directional derivative, in the direction of a certain vector, you should think, okay, wait a minute, what do they mean by that? If you're not clear, if you can't figure out for yourself which they mean, ask them. And then arguably even worse, make sure to realize that if you make a reference to a directional derivative, then they might misinterpret you. So might be worth clarifying in that case as well. Yes, you had a question.
Yeah, so just to clarify, you're doing gradient dotted with a unit vector. So because you're doing a dot product, it's going to be a scalar, but because it's with a unit vector, it's going to have variables in it, which is why it becomes a function.
I'm not quite following the point I'm trying to make here. What I'm getting at is the unit vector requirement is essential to get these properties. That was all I was saying here.
So when we take directional derivative, what is the output? It's not the number 5, right? It's like.
No, it's a number. Yep, it's a number. It's a.
Can we also get a general one?
Oh yeah, if you take a vector here, I'm just talking about a real valued function f. But yeah, if you want to talk about a vector valued function f, then yes, this formula still makes sense. This notation still makes sense. And you'd have to do the matrix version of this because there's no dot product. Yeah, right. But keep in mind, here, let me write down, if we were to scratch that off and say df at a times the vector v, this works just fine. Vector valued or scalar valued, take your pick. But in practice, day in and day out, when you're talking about real valued functions, which most of the time, when you talk about directional derivatives in practice, most of the time you're talking about real valued functions. And in those cases, it's kind of easier to think of it that way.
What do you mean by real value?
It means that the values of the function are real. They're real numbers. Yeah, as opposed to vectors, which is, what you get when you talk about a vector value function. Yeah, there's some pages in the notes on this back in to the first couple of pages of 2.1. Yeah. Is that cool? Yeah. Okay, we're almost out of time. Good night. Okay, so let's see here. Let's not be heroes here. I'm going to just draw a line right here. Quitting a minute early. I'm sure I owe you the minute. See y'all on Friday for the test. Good luck in your studying, and see you then.